Hey there, welcome back. Welcome back to the channel. So this is Ramandeep Singh, and we will continue in that CSES problem solving sessions. And in this particular session, we'll be solving the next problem in the series, and the problem name is message routes. Right? We'll solve message route. I think this is the fourth problem in the CSES problem set, graph algorithms, and we will be solving this problem in today's session. This problem is also really like easy, just DFS and BFS problems. So basically in graph algorithms, the most primitive algorithms you can think of are depth first search and breadth first search. You must know how to perform a depth first search over a graph, how to perform a breadth first search over a graph in order to solve some primitive level problems on graphs. Okay. And if you don't know, please go and learn those algorithms first, then you come back to the problem solving things. Okay. So in this particular video lecture, we'll be solving this message routes, and without wasting more time, let's jump to the problem statement. So here there, let's start solving this problem message route. We have a network of n computers and we have m connections among them, and the task is to find out if a character ULV can send a message to Maija, if it is possible. And if it is possible, we want to figure out the minimum number of computers on the route from the ULV up until Maija, right? So let's see how we can solve this problem. So we have been given these 5 computers, and so we have these 5 computers. Let's take the first example. We have been given 5 computers and there are 5 connections between them. So there is a connection between computer 1 and computer 2. There is a connection between computer 1 and computer 3. We have a connection between computer 1 and computer, so we can write it like this, 3. Then we have a connection between 1 and 4 as well. Then we have a connection between 2 and 3. So we have a connection like this, and like this connection is here. Then we have a connection between 5 and 4. That's all. So these are the connections that we have: 1 2 1 3 1 4 and 4 5. Now this is the source computer, which is computer number 1, and the destination computer is computer number 5, or the computer number n in a graph of n nodes and m connections. So here we have a graph of 5 nodes and 5 edges, and we have a starting node which is 1, we have an ending node which is n, and we want to send a message from the starting, and the message should reach the ending node n, and it should pass through minimum number of intermediate computers. Like here in this case, the best path would be 1 4 and 5. The message starts at 1, moves to 4, and then finally moves to 5. So it covers 3 computers, including the source and the destination computer, right? So the minimum number of computers that we require in a particular message route would be 2. We can't have routes less than 2, right? Why? Because we have, I think, at least 2 nodes in the tree, in the graph. Yes, we have 2 nodes, and in that case, in the graph of 2 nodes, the message starts at one node and ends at another node, right? So the minimum possible length of the valid path would be 2, and the maximum would be n cost, right? Now for this particular configuration, we want to find the minimum number of computers that the message has to pass through in order to reach the destination, while starting from 1 and ending at n. So how do you solve this problem? Think about it. So it's nothing but a shortest path problem. This shortest path problem. We are basically calculating the minimum number of intermediate computers or intermediate stations or intermediate computers in order to reach the destination node. So how would we solve this? Since the edges do not have any weight, we can see the edge weight is 0. Not 0, like we can say 1. The edge do not have any weight. we just have to count the number of nodes. So we can simply use BFS for these type of problems, like breadth first search. Why do we need BFS? Why we use BFS? So that is a matter of different discussion, not now. I am here in this particular session or in these sessions, not focusing on teaching you why to apply X algorithm for Y problem, right? Yeah, I may explain you, okay, this was the intuition, but actually you need some memory before you start solving these problems. The memory, like, what is BFS, what is DFS, what are graph algorithms, the standard graph algorithms, that I'm expecting you people know before you start solving these problems, right? If you're starting from really scratch, then I would really recommend you to just learn breadth first search first, how the breadth first search works. Once you understand really well how BFS work, the solution for this problem becomes immediately available as the breadth first search. Why? Because the idea of breadth first search is simple. You start from the source node. Now you visit all the nodes which are present at the next level of the source node from where you started, right? So you started from 1, that was the first level, the level you started with, let's call it level number 0. Now what are the nodes at the next level? The next level nodes will be the neighboring nodes of 1. The nodes are 4, 2 and 3. So if 1 is present at level 0, then node 4, 2 and 3 node 4, 2 and 3 are present at level number 1, right? Now from 4 and from 2 and then from 3, from 4 I can move to 5. I can't move back to 1. Why? Because 1 is already visited. So we also keep track of the visited nodes, right? So we have a, let's say, visited array, and in the visited array, since node number 1 was visited, so we mark it as true. Let's call it T. T for 1 means it is visited. Now 2, 4 and 3 are also visited. So 2 is visited, 3 is also visited, 4 is also visited. 1, 2, 3, 4 are visited. Now from 4 I can move to 5. I can't move back to 1, and the check is here, this array, visited array. I can see that 1 is already visited. 1 is already visited, and we can't move back to 1. And 5 is not visited. 5 is not visited. So we can move to 5. So from here I can move to 5. 5 is present at level 2. Then from 1 I can also move to 3. I have already moved to 3. From 2 I can move to 3, but I will not move to 3. Why? Because 3 is already visited. I can see that 3 is visited here. True. So I will not move back to 3. Right. Now at this point all of the nodes are visited. I can't visit any neighbor node of node number 2. I have visited the neighbor nodes of node number 4, and I can't visit the neighbor nodes of node number 3 as well, because what are the neighbor nodes of node number 3? 1, it's already visited. 2, it is also visited. So we will end our BFS right here. Now we have visited all the nodes and we have the levels for each node, and what we have to do, how many nodes I visited in order to reach 5. Now 5 is at level 2. 5 is at level 2. What does that mean? I must have started from 1. I moved to one level next to 1, that would be 4 and 2. Now I crossed one more level to reach 5. So I covered 2 levels. The first level was at 2 and the second level is at the destination node. So if we have covered 2 levels, that means I must have visited 3 nodes to reach that level, right? I must have visited 3 nodes, including the source and the destination. The source was 1, and now I moved to the next level, which was 4. So I covered 2 nodes here, and then I moved to the final destination node and I covered 3 nodes. So if the levels are 2, then the nodes would be 3. So the number of nodes, levels plus 1, right? So that's all we have to do. Just perform a BFS. starting from this node, which is the source node, and figure out the level of the destination node, and the level plus 1 will be the answer, right? Let's jump to the code implementation part. Okay, so from here I'll have to move. Let's jump to the, what is the input? Input is n and m, and then we have m lines, which represents the connections, and yeah, that's all. Yeah, there can be a case when we are not able to reach the destination. In that case, you will print impossible for that case, right? And the output format is simple. First print k, the minimum number of computers on a valid route. After this, print the actual nodes through which you are hopping in order to reach the destination. So I think everything else is same. We are reading the graph, and yeah, we are reading the graph, and then let's erase this. Read n and m, number of nodes and the number of edges. Read the graph in the adjacency list. Then we have a visited array, and now I will need a q. Let's call it q, and we also need a distance vector, and let's initialize it with a very large value. Let's call it int max, and the distance for the source node would be, the source node is 1, let's take it as 0, right? The distance for the source node will be 0, and push the source node into the queue. Now iterate over the queue and retrieve the node q.front, q.pop, and it was visited, so mark it as visited. Visited for 1 would be true. Now what can I do here? I'll iterate over its neighbor nodes, adjacency list of node. If the neighbor node is not visited, then what I'm going to do is I'm going to push this neighbor, and I'm also mark it as visited for the neighbor. I am also going to update the distance for the neighbor as the distance, like min of distance for the neighbor, whatever we have, comma distance of the parent node, which is this, plus 1. Okay, and that's all. Mark it as visited, and yeah, that's all. And here you're gonna print. Now if this distance of neighbor is still int max, what does that mean? We were never able to reach the destination node, which is n. Distance of n is equal to int max. You see, the int max initially contains int max. This distance array initially contains int max value for each node. That means every node is present at an infinitely large distance from the source node 1. Now if the distance is int max, I'm going to print impossible and return from here, right? Otherwise I'm going to print what? I'm going to print the क्या print करना अपने को? What do I have to print here? The distance, right? Yeah, the distance I'll have to print, and that would be present here at distance array nbr, not nbr, distance for n plus 1, like this. This is nothing but the levels, like how many edges, how many minimum edges far away the source is, the destination is n. But we also want the exact trajectory or the actual path which we have covered. For that I will use a parent array of size n plus 1. Initially it contains minus 1. Parent array means parent of node contains the node from where I reached this node, the immediate previous node. We can also say it as immediate previous node. That's the parent. Now don't confuse it with the parent child relationship of the tree. That is a different thing. That is a two-way relationship. Although this is also two-way relationships here, right? It's a two-way, yeah. But don't confuse it with that, right? We can like, for a better, we can also say, the neighbor. Instead of parent, we can also take as the previous, let's take it the previous node. That's the better word to use for this array. Okay. Now here for this we have and here when I am visiting the neighbor of any particular node, this particular node I am visiting its neighbors, then for that neighbor the previous for the neighbor become the current node, right? And if I am reaching at this point and the destination node is n, so until the destination node n do not become minus 1, what I am going to do, I am going to print previous node of n, right? Or let's print n with space and reassign previous of n to n. So it's more of like, think about it, this previous at this point, so the previous array will be constructed like this. Let's first move to the dock. So for this particular graph, how will the previous array look like? The previous array will look like this: minus 1, then we will have for 2 we will have 1, then for 3 we will have 1, then for 4 we will have 1, then for 5 we will have 4. This is how the previous array will look like. That means for node number 2 the previous node is 1, for node number 3 the previous node is 1, for node number 5 the previous node is 4. And now I start printing from the last node, or let's say I start tracing the path from last node. So I start from 5, the last node is 5, I move to position 5, 1 2 3 4 5. So at 5 we have 4. That means the previous node to 5 was 4, so I push 4 here. Now I move to position 4, 1 2 3 4. Now the previous node from 4 was 1, so I push 1 here. And now I move to 1. Now the previous node from 1 was nothing, there was no node before 1, so we have minus 1 here. So this is the path in the reverse direction that we need. Now I'll print this path in the reverse order: 1 4 and 5. That's my answer. That's what we have to do here. Okay, that's what we have to do here. And I think I'll have to print this in the right order, no? 1 4 5. Okay, so I'll need one more vector. Let's call it path vector. So let's, instead of printing directly, let's push n, and then finally you're gonna push path. You have pushed enough. Let's reverse it. Reverse path dot begin path and for path, right? I hope it is clear to you. First n will be pushed, then yeah, until n do not become, all of the nodes will be pushed. That's fine. I think it will give correct answer. Let's try running it. I don't know what happened to my Sublime text editor. It is not working really. नहीं इसको क्या three one four five, yeah, that's correct. सबमिट करते हैं इसको. ठीक है, it got accepted. That was an easy problem, just a simple BFS skill. And let's see if let's just see if let's analyze the time complexity for this. Now the time complexity for the breadth first search is big of n plus m. Now it's, since it is a graph, I'll have to include the number of edges, because you may get a complete graph where the number of edges goes like quadratic time complexity of the number of nodes, like that's n square. And the space complexity would be big of n, because we use q in the breadth first search. So I hope this thing is very very clear, and I'll see you in the next one. Till then, bye bye. And try solving the next problems by yourself. Try solving, like, now once you have learned about breadth first search. I think, yeah, try solving this problem, labyrinth. Try solving labyrinth. And this is also an easy, similar problems. You can also try solving the next problem, I think, building teams. Achha, I think this problem is bipartite graph. I'll solve it in the next session. But that's all for this video, and I'll see you in the next one. Till then, take care. Bye bye, ladies and gentlemen.